Okay, so let's continue about how to generate the loop structure, not loop function. Okay, so last time we learned about the two instruction. One is jump and link instruction and jump register. And jump and link instruction is storing the current PC value or next PC value in, so generally the next PC, but in the MIPS case it is PC plus 8, right? So after calling the function, the next instruction is stored, and then PC value is changed to the label. Jump register case, it is looking at the sum register. Okay, so you, and also we learn about the stack. So when function is called, the stack should be manipulated. Okay, so let's look at some example then. Let's look at the first one. It is calling function f, which for the argument we are passing 3 and 4, and then inside this function it is comparing, and then it is returned. Okay, so then let's write the assembly code for that function. So integer f, a and b, and inside of that it is only returning. And then there is main function. Main function is also function. F3 and 4. Okay, so how we can generate the code? The first function f, we are creating the label f, and then there are two arguments, so which means that we can use the register as parameters. So the first one is storing the A0 register, second one is A1 register. Okay, so it's right there. And so we just need to compute the comparison. For the computing of this less than, which instruction do we have to use to compare? Which instruction do we have to use? Yeah, set on less than instruction. Okay, comparing A0, A1, and which register do you have to store that comparison result? Yeah, V0 is returning address. Okay, we already know that array register is containing the returned value, right? Okay, and then so we don't need the stack in this case because there is no local variable. So we just do the return. Okay, and no operation. It's done. So that's the code of function f. How we can generate the main function? Main is also function. Okay, so there's nothing. We just need to setting 3 and 4 as argument for the function f. So add I A0, 0, 3. Add I A1, 0, 4. And then we have to call function f. So jump and link and operation. It's done. Okay. So can you write this code in the simulator? But when you are writing the simulator, you have to write the main code first, because in the simulator, the first instruction is automatically run. Okay. So you are writing the first one, and then you are writing the f after that. Okay. So open your simulator. And start to write the code. So if you are completing, then write down the what's the V0 register value. So you maybe write this kind of code, right? So writing the first main code and then writing the function f. So if you're running this code, okay. So you know that there is a stack pointer here, right? So register number 29 is a stack pointer, but we are not changing the stack pointer at all. Okay. And if you are pressing the step, so A0 is 3, A1 is 4, and then jump and link is jumping actually. Okay, so A0, A1 is compared, so it's true, so V0 will be 1, and then it is jumping back. Okay, so it's jumping back, so after no operation, it is jumping to here. Okay. Okay, then let's get the second example. So we write the code, right? We can write the code. So main is equal. So main is equal to the previous one. So can you write the function g in the chat window? Can you write the libs code for the function g? Okay, somebody is asking me that in general, we are just using the V0 register only, right? But actually there are two registers, V0 and V1. So which case we are using the two registers? In C code case, if we are just using the integer, then we don't need to use the V1 register at all. But if you are using, instead of int, we install like a long. So this is actually 64-bit. So return value is more than 32-bit. In that case, you have to use two registers. Okay. So most case you just need one register for the returning value, but in some case we need two registers. If the returning value is requiring the more than two register, in that case you have to use memory. Okay, so you have to store the result into the memory, and then you have to give that the address of the memory location. Anyway, can you write the MIPS code for the function G in the simulator? And if you are finishing, please upload the code in the chat window. Right. Okay, it's very easy, right? So first is G, then is doing the addition. Add I. So return is V0, argument is A0 and A. And then jumping back to the array register. That's all. Okay. Okay, so now let's look at the function f. It is more difficult. Can you write the MIPS code for this function f? So you have to write down the f, right? So what do you do? What you have to do? So you are maybe calling the function g, right? Because the first a is actual argument of g. But if we are calling the jump and link, then what is happening? Then array register will be destroyed, right? So before we are calling the jump and link, we have to store array value in the stack. Store array in stack. So in order to do that, what you have to do? First, you have to increase the stack. Actually, increasing means decreasing. Right? And then storing the array value in the stack. So can you write the code? So this case, jump and link, no operation. So then GA V0 will be containing the result of function G. So we have to 7 less than V0 with A1 V0 and then return. But before we are returning, we have to restore the array register. from stack. And then stack pointer is restored. And jumping to the original location. Operation. Right. So here in this case, we are storing the A0, right? We have to store the, we don't need to store A0 because it's already there. Okay. But actually, when you're writing the code, if we don't know about the information about the function G, in that case, we also have to store the A1 register value because A1 will be destroyed if we don't know the function G part. But anyway, this code is working. Okay, so can you write the MIPS code for these functions? And then what is the result of V0? So what's the result of F 3,4? It's called. So write your MIPS code in the chat window and then specify V0 register value. Can you also upload your code? Okay. So let me show you some result of that example. There are three functions, main and on the by f function f, and function g. Okay, so I just put the many no operation to see where is the current location. Okay, so just for the distinguish each functions. Anyway, so we are starting the code. Then, okay, so first A0 is 3, A1 is 4, and jump and link is called function f. Okay, so 4, and then jump and link, this is called. And as you can see that stack will be changing. Okay, so 0x7ff8. Let's go to that location, that memory location. Then you can see that there is nothing, right? Everything is 0. Okay, then let's do the store. So store operation. And you can see that array value, which is 00040010, that is stored in this memory location, right? So store operation is storing the array value in this stack area. And then it is calling jump and link and G. So the operation and jump and link value will be changing to this location. Actually, the next one here. So after this location, so current location is 40028. So next one is +4, which is 4002C. So that is stored into the register, and then it's jumping to this location. Okay, so pre 0 will be 3 plus 8, which is 11 with B. And jump and link is looking at this location. So this location is actually, where is it? Number 12. So line 12. So it's going to the line 12. Okay, here. And V0 is containing B. And B is comparing with 4. So it's false. So V0 will be 0. And then return value will be restored from this location, stack location. Restored. And then stack will be changing. Stack pointer is changing. Okay. So stack pointer is pointing here, actually. This is top place. And then jump and link array register value, which it will be, I think, number 5. So it's going to number 5. Okay. So this is just keep going. So this is the code. Okay, so last thing is recursive call, but I think you can also do that, right? Writing the MIPS code for this one. So I will give a homework for this third one. Okay, so it's just summation of integer numbers. So I think you can write the code for that example yourself. Okay, so any question about the function call? Nothing? Okay. So main question in the midterm exam will be writing the C code to the MIPS assembly code. Okay, so most of the question will be this kind of translation. Okay, so we did it. So we learn about the two instruction. One is for the memory access. One is load word and store word. So it is word unit memory access. So in some case, you just want to store the 1 byte or load 1 byte from the memory. Okay, or you want to store the 16-bit load and store. So in that case, you can use some different instruction like load byte, store byte. The format is the same, load byte, like a 0 register into some location. Then actually this register is containing the 4 byte, right? It's containing 4 byte, but among these 4 byte, only 1 byte, last byte, is stored. Not this one, first one. This is stored. Okay. Load case, it is just loading. Okay, so not this. So there is a register A0, and there is memory here. Memory. If load byte is called, then it's looking at that location. So there is 1 byte here, right? So many byte here. So that byte is loaded, and then stored into the last byte location in the register. Store byte case is also same thing. The 0 is there. Then there is some value. Then that 1 byte is stored in that location, specific location. Okay. So similarly, load half word, store half word. Okay, that's a half word. Okay. So it is storing the 16-bit. So 2 byte are loaded or stored if you're using this instruction, LH or SH. Okay, so we learn about this byte operation also. Then you may be implementing this kind of functions. So which is a string copy. String copy. So it is copy data from Y to the X. Right. So in C code is like this. So it's like just for loops. Initialize, and then Y value is copied to the X until the last. So Y value is reaching to the null, 0 value, then it is terminating. Otherwise, we are increasing. So if we are writing the string copy, this pointer actually. Let me write down the for I equals 0, and then xi is assigned from the yi. Not this one. Maybe which is better. Just write the original code. I equal 0, 1, xi is y, I, which is not 0 case, then I is increasing. So this is given code. So let's try to translate to this code. So what do we do? This is address, right? This is address. This means address. So there are two arguments. A0 is containing starting address of X. A1 register is containing starting address of array Y. Okay. So anyway, so first we have to string copy. And we have to specify the stack, right? So we don't know we need the stack manipulation or not. But anyway, we leave it as empty. And then we have to initialize I. So let's try to initialize. So we need a temporary register to use for this local variable. So there is some temporary registers, T0 to the T, how many temporary registers? 10 temporary registers. So you can use this temporary register for the local variable. So T0 is initialized by 0. Okay. And then we have to do this part. So what do we do? Y index. This is actually load from the memory. Okay. The type of Y is character. So we have to learn the load byte. Okay, so because it's Y is one character value, so we have to call the load byte instruction. The location for this address, so Y plus I. So we have to compute this part, right? So before we are calling the load byte, we have to add A1 with T0, and then into the T1 register, and then load byte. T2, 0, T1. Okay, so that's the new address. So we are loading 1 byte from the memory. After that, we are copying into this location, memory location. In order to do that, we have to compute address. So we have to compute X plus I. So X plus I case, because X is a character type, we don't need to multiply the 4, right? If X is an integer type, in that case, the address is X plus 4 times I, but this is character type. So we don't need to do that. And X location is A0 and T0. And then it is T3. That's the address, and then store byte T2 value into the T3 location. Okay, so we are completing the storing the value into the XI, and then we have to compare with 0. So we have to use branch equal or branch not equal. So I don't know which one. When we are exiting from this while loop, if this is equal to 0 case, we have to exit, right? So we have to use branch equal. So T2 value is 0. In that case, we have to exit. Okay. Otherwise, we have to increasing the I value. So increasing the I value, we are calling add I. So I is in the T0. Okay, so I plus plus is implemented. After that, we have to go to the while loop again. Back to the while loop. Okay, so we have to jump to the. So which place we have to put the loop label? It should be here, right? So that part is actually computing y plus I. The part updated. Okay, so in this code, we don't need any local variable, where this function is not calling another function, so we don't need stack, right? So we don't need stack. So we are just, after this one, we are just returning. That's all. Okay. So maybe this code is really different from the next slide, because next slide case it is storing the some value into the stack, but we here in this example we are not doing. Okay. So we learn about the load byte and store byte, load half word, store half word. Okay. Now we learn about the immediate instruction, add I instruction. Okay, so this instruction case, we are specifying like this: T0 register 0 and something is constant value. But this constant value can be up to 16-bit. It's a 16-bit, which means that T0 is actually 32-bit. So by adding these two values, we can fill the 16-bit only. So then how can we pad another 16? Right? So we need that one. So one way is that you're calling this add I and then shift the 16-bit to the left. So shift left logically T0 and 16-bit into the T0. That means after that, this upper 16-bit is filled. And then you are calling another add I, T0, T0, and this part is called. Okay, so here another constant. Then you can make a 32-bit value. So here in this case, you have to call the 3 instruction. These 2 instructions, actually it is just storing into the register from the 16 constant value. So for that one, there is another instruction, which is LUI. Actually, it is load upper half word immediate, but actually this is not the load instruction. Okay, so it's not load. The instruction. It is actually add I plus shift left logical instruction things. So T0, like just constant. Then this instruction is storing the data into upper location. Okay. And then you have to fill the lower one. To fill the lower one, you can use add I. Or anything is okay. Or I. It is also possible. So or is in this case because we are adding 0 value. So up, lower part is 0. So you can use this or I. Okay. So load upper immediate. So using these 2 instructions, this instruction and so one of them, you can make a 32-bit register value. Okay. So we will look at the format of the instruction. So we'll learn about the 2 formats. One is R format and I format. So R format case, 60-bit is operation, which is 0 actually. And then S, source register, temporal register, and destination, and some shift amount, and function. Function is actually representing the operation of the instruction. I format case, 60-bit operation, and RS, RT, and then 16-bit immediate value. Okay. So belonging to the I format is load store is belonging to that instruction, add I, and I, or I, these instructions also belonging to the I format. So let's look at the branch instruction. Branch instruction, branch equal, branch not equal. What's the format? Branch equal is specifying 2 instructions, like T0, T1, and then we are specifying label. Okay, so we are specifying 2 registers and 1 constant value. So this is which branch is belonging to the R format or is belonging to the I format? Yeah, it is I format. Okay, so branch equal, branch not equal. It has its own operation. Okay, and then 2 register, source and destination, And here it is address or constant value, 16 bit. Okay. So this is just constant value. Or let's say this is offset, some value. Okay, so the PC that is addressed to be jumping is 32 bit. But this part, the constant value is 16 bit. It's not matched, right? So when the branch equal is called, we have to compute where is the target address, where we have to jump target address. So we have to computing target address PC, new PC is from how to we are computing using this information. So branch instruction case, it is using the relative address mode. Relative address. That means the new PC value is based on the current PC value plus the offset value. But we know that one instruction is 4 byte, so it is multiplied by 4. That's the new address. Because PC is increased by 4. Okay. So new PC target address is PC plus 4 times the constant in the instruction. Okay, then let's look at the branch equal 0, 0 in some label. And there is some label. And we are just putting some operation here. Okay, so let me write down the code in the simulator. Okay. So branch equal 0, 0, some operation, operation, operation. There's a label. I'm running this code. So let's look at what is happening. Okay, first one, PC value is 40000, right? So that's the starting point. Okay, so next step is comparing these two register value. So that is equal, right? So that's equal. Let's look at the instruction. Okay, so 10000006. So 6. So let's look at these two instructions. Where is the, how many instructions do we have to pass to reach the label? So +1 is next instruction. 1 + 1 + 2 + 3, 4, 5, 6. So this loop is, the label is after 6 instruction, right? After 6 instruction. So the constant value is 6. So this value is 1. That means branch is jumping to the next instruction. If it's 2, then it is jumping to the next instruction. Okay. So then let's look at how the PC value is changing. Instead, now it's jumping to 18. So when the branch equal instruction is called is 400000, right? And instruction was the constant value is 6. Okay, so 6 times 4, which is Yeah, 24. In the hexadecimal is 18. So 18. So 18 is in the hexadecimal, 18 is in 24 in decimal. Okay, so it's jumping to this location. Okay, so if we are removing or adding 2 more instructions, okay, so then you can see that the instruction, jump branch instruction is containing number 8. So after 8 instruction later. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. If branch instruction is going back, what is happening? So label is here. So let's look at what is happening. Okay. So this case, branch instruction is going back, right? It's going back. Okay, so nothing is happening. Okay, can you guess what is the constant value in this case? How many instructions we have to go back? 1, 2, 3, 4, 5, 6, 7, 8. So it will be -8. It will be -8. So, but we have to change in the two's complement representation step. So F8, it will be -8. Okay, because if we are adding 8 here, then it will be 10000, right? 10000. If we are adding the 8, that means it is -8. Okay, so if you are going back, then the constant value is negative. If you are going forward, then constant value is positive. Okay. So that's a branch instruction. Then let's look at the jump instruction. Jump instruction. So jump instruction is jump. Okay. Jump instruction case, we are just specifying label only. Where jump and link, it is also we are just specifying the label. So we don't need to specify register. Okay. So jump instruction case. So for the OP code, we need spend 6 bit. And remaining part, we don't need to specify anything others. So this is actually address. This is constant value. So 26 bit is used for the constant. Okay. So then we need compute target address, new address for this jump instruction. So PC value should be updated. Okay. So PC is 32-bit. But this address is 26-bit. So we have to change it from 26-bit to the 32-bit, right? So branch instruction case, we're just adding PC value with this constant value. Jump instruction case is not adding things, it's different. Okay, so how we are doing this thing is simply we are assigning address. But we know that address is increased by 4, right? So we are multiply 4. Okay. So that means from this 26-bit, so this is 26-bit. This 26-bit is filled by this address. And last 2-bit is 0. Okay. Multiply 4 means the last 2-bit is 0 because we are just left shift, 2-bit left shift. But still, how many bits do we have to fill? Total should be 32 bits. So how many bits are still remaining? Yeah, 4 bits. So which bit do you want to use? What kind of value do you want to use for this 4 bit? Just filling 0? What do you do? So here in MIPS case, the original PC, old one, has some values, right? PC has some values. Among this PC, there are 4 bits is here. Okay, so the most significant 4 bit is copied into the location. So when we are computing the target address, the upper 4 bit is from the current PC value, and remaining part is from the constant value. Okay, so combining the 2 things. So lower 28 bit is from this address, and upper 4 bit from the PC, old PC, from 31 to the 28. So 31, 30, 29, 28. This 4 bit is copied. Okay. That's the new PC value for this jump instruction. Let's look at some example. So let's look at this example things. So here, left one is this code. So let's look at 2 instructions: branch not equal and jump instruction. Okay. So branch not equal. Where's the exit? So this is exit, right? So how many instructions do we have to pass? 1 instruction, 2 instruction, and 3 instruction, right? 1, 2, 3. So branch not equal case, plus 1, plus 2, and plus 3. So it will be 3. Okay. So it will be plus 3. And jump instruction case, jump instruction is OP code is 2. Okay. And the constant value loop is here. Okay. So in this case, we have to look at the absolute address, A0000. Okay, so let's assume that this is A0000. So what we are assuming is, so A000 means in the binary 1 0 0 0, that is A 0 0 0 0 0 0 0 0 0 0 0 0 0, right? That's the address. So now when we are making the constant value, we know that the last 2 bit is always 0, so this 2 bit is just removed. Okay, so divide by 4. So like divide by 4. This is new thing. So it will be value 2 0 0 0. That's the constant value. Okay, so 2 0 0 0 0. That is constant value when we are making the PC value 20000 multiplied by 4, which is 80000. And then the upper 4 bit is from the PC value. So the upper 4 bit is actually 000 in this case. So this 000 is copied into this location. Okay. So when jump instruction is called, that jump instruction is actually jumping near to the current PC location. Okay. Because the constant value is not 32-bit. Then maybe you want to jump really far from the current location, right? You want to jump really far. So how can you do that? If you want to jump into the very, so here this is the current location instruction, but this want to jump into very far. Okay? So in the case, what do we do? In the case, first solution is we are using the jump register instruction. Jump register instruction case, we can setting the register value, right? Register value is 32-bit, so arbitrary value can be set. Second one is, it is only jumping to the 28 address space. So it is jumping to some location here, and then this is jumping to here, and this is jumping to here. So we are jumping several times. Okay. Branch instruction case, it is much smaller, right? Branch instruction case only 16-bit. So from this location, it can be jumping to the 2 to the 15 and 2 to the 15. So if you want to jump into more, in that case, what you have to do is you have to specify jump instruction here. And branch instruction is jumping to this location, that instruction, and jump instruction is actually jumping that location. Because jump instruction can support 26-bit. Branch instruction is only supporting the 16-bit. Okay, so this kind of approach is used. So 16-bit actually, how many? The 16 is 64 kilo, right? So if your program is larger than the 64 kilobyte, then branch instruction is not jumping to more than 64 kilobyte. So if you are jumping like 1 megabyte later, in that case, you have to use two instructions, branch and jump, or you have to use branch and jump register instruction. Okay. So addressing mode is summarized here. Operation is looking at the register, which is jump register instruction. In this case, register value is target address. Branch instruction, two register is specified. And then here there is constant value. Then in the case, the target address is adding of address with PC value. Actually, this is this one, PC value. Okay. So this is branch. And then jump instruction case, then the address part is concatenated with PC value 4-bit. So from the PC, we are just copying from the upper 4-bit, and then address is copied into the smaller part. And base address mode, it is load store instruction, load some address. In that case, target address is computing register value plus offset value. Okay, so these kinds are supported. The first one is just immediate value. Okay. This is mode. So we are complete the chapter 2. Okay, so it is talking about the instruction set of the MIPS architecture. Actually, I uploaded the full instruction format in our RMS system. So there is another PowerPoint, which is explaining about the format of MIPS instruction set. So if you are interested in the instruction set, you can refer the slide. Okay. Okay. Any question? Okay. So I will upload the homework in this week. So for this translation of the C code to the MIPS code. Okay. So see you next week. Bye.